Good morning, children. So, in the last class, I've explained you about logic gates, the basic gates, advanced gates, and universal gates. So, today we'll discuss about application of logic gates. So, what does application means? Application means uses. In which field logic gates are used? Actually, logic gates are digital circuit. They are used in different purpose, where electronic or digital concept are there. But they are categorized in four different fields. Number one is adder. Again categorized two part, half adder, full adder. Then we have encoder, decoder, multiplexer. Multiplexer. Or multiplex also you can say. Multiplex or multiplexer. So there are four different types of applications where logic gates are used. Multiplexers are even known as MUX. So children, now I'll be explaining you in detail about adder. Okay, so see here. So now in adder, first of all let me tell you what is the use of adder. Like in every CPU in the processor, there is one ALU, arithmetic and logic unit, which does all the calculations. But remember one thing, ALU only does binary calculations. It does not perform any calculation or any operation on decimal numbers. In the same way, adder also work on binary part. Adders are categorized in two parts, as I have already listed there. So first one I'm taking as half adder. So what is half adder? Half adder, it is used to perform addition on two bits. Addition on two bits. Now let us go in depth. First of all, truth tables of half adder. Let us take two variables, say a, b, and or let us take xy or a, b, any variable you can take. Let us take xy only. So xy and the adder part. Adder part will be carrying sum as well as carry. So let us take this one as input and this one as output. So this is the structure of our truth tables. Since we have taken two variables, so I will take 0011. Now if you remember the addition rules, 0 plus 0, sum 0, carry 0. 0 plus 1, sum 1, carry 0. 1 plus 0, sum 1, carry 0. Now 1 plus 1 is what? 1 plus 1, remember the arithmetic addition of binary. So whenever we get 1 plus 1, sum is 0, carry is 1. Is this clear, children? Sum 0 and carry 1. So this is the truth table of half adder. Okay. So now from here we'll take out the sum part and carry part separately. So when you take out the sum and carry part separately, you have to just check the variable as 1 because 1 is for on bit. So how many 1 we have in sum? 2. And how many 1 we have in carry? Only 1. So the corresponding variables we have to check. So first let us check the corresponding variable for 1 in case of sum. Now when you check the corresponding variable, few rules again you need to follow. Few rule is what? Now in the input side, 0 is complement for that particular variable. Okay, and 1 is non-complements. So first of all for this variable, this 1. So what we have? X value we have 0 and y value what we have? 1. So x will be complement and y will be directly. Now since it is addition, so plus, we'll move to the second part. In second part again if you see, x is normal and y is complement because y variable value is 0. Is this clear, children? Now in the same way let us move to the part of carry. So when you move to the part of carry, again you have to check the 1 and its corresponding input variables. Both x is also 1, y is also 1. So xy. Now according to the law, x complement y plus xy complement is known as x or y. Now what is x or y? If you remember, XOR is the advanced get, exclusive or get. So x complement y plus xy complement is known as x XOR y, and carry is simply xy. So when we get the Boolean algebra for sum and carry, we can make the logic circuit diagram. So logic circuit diagram, when we make, we have to just check the variables. How many variables we are working on? 2 variables, because we are doing with half adder, which perform addition on how many bits? 2 bits. So x and y. Okay. Now see children, for sum what we have? X XOR y. So XOR means exclusive OR get. So OR get means we'll take out the line from x and y and we'll make the OR get. But since it is exclusive OR get, so here double part will be there. So this part will be known as x XOR y, and it is also known as sum. And for the carry, x and y we have. So I will take for x and I will take for y, and I will make the AND gate, that is x dot y. This is known as carry. So children, understood? So this is total about half adder. Okay, now in the same way we'll move for full adder. Children, now see, for full adder. Full adder, it operates on how many bits? 3 bits. Okay, so full adder is used to add 3 different bits. So now let us go for truth table of this one. If you take again x, y, z as input, so input let us take as x, y and z, and output will take as sum as well as carry. So since it is for 3 different bits, so first we'll be having 4 0, then 4 1, here 2 0, 2 1, 0 0 1 1, then single 0 1, and based on the binary addition calculations will get the value of sum and carry. So here 0 0, then 1 0, here also 1 0, 1 1. So when we get 1 1, that time sum is 0, carry is 1. Single 1, so sum 1, carry 0. 1 1, so 0 1, 0 1, and when there are 3 ones, sum also 1, carry also 1. So is this clear, children? So this is the logic how truth tables are generated in the same way like what we did in half adder. Okay, only the difference is that in half adder there will be 2 bits and in full adder there are 3 bits. You might be wondering what exactly is this? It is a power socket. See, when electricity is, any power socket board are there, you will find any appliances, any electronic appliance, they have either 2 socket or 3 sockets plug. Okay, so when they are using 2 1, that is half adder concept they use. When they are using 3 1, full adder concept they use. Now Boolean algebra we have to take out, that is sum and carry. So same way we have to consider the one part like this one. Okay, so when we go for the sum part, we'll be having first case, that is x complement y complement z plus. Second part, x complement y z complement. Third part, that means this one, So x y complement z complement, and fourth part is x y z. So again, exclusive OR gate concept is used here, and it becomes x or y, x or z. Okay, this comes from exclusive OR gate. Now come to the part of carry. So carry part means this one will be having x complement y z plus x y complement z plus x y z complement plus x y z. This one is again following the exclusive OR gate concept. So you can see here x complement is here. Here we have y complement, here we have z complement, and at last we don't have any complement. So this we can write directly as xy or yz or zx. So we can write in this way. Okay, xy or yz or zx. Or we can write in this way also, plus yz plus zx. Okay, so now see here we got the sum boolean part as this one, and the carry boolean part we got as this one. Now is this clear, children? So we got the boolean algebra part of sum and carry. Now we'll be designing the logic circuit diagram for this one. So see here. Now we'll be designing the logic circuit diagram from the boolean algebra part of sum and carry. Okay, for full adder only. So logic circuit diagram. So how many variables we have? We have to check that first. In both the cases, we can see we have only three variables, that is x, y, and z. So x, y, and z. So we'll do this one. Now the sum part x, x or y, x or z. That means x, y, z, and x or y concept will be using. So it will become as x, x or y, x or z, and will give name as sum. And the carry part we can see here, we have xy, yz, and zx with some part, that means OR part is there. So first xy, then second we have is yz, and third we have is zx, z and x. Now see, these three different gates, AND gates, because x dot y, AND gate is there. Okay, now these AND gates are joined together with the help of OR gate. So OR gate, this is xy plus yz plus zx, which is known as carry. So this is all about this z. Okay, so children, this is all about full adder. So sometime you may get the question, what is the difference between half adder and full adder? Okay, so you have to first give that half adder is used for adding 2 bits, full adder for adding 3 bits. Then you have to draw the truth tables, you have to draw the logic circuit diagram only after take outing the Boolean algebra part of sum and carry. Is this clear, children? So next we'll move to the part of another topic, that is encoder. So children, next logic application of logic gate is encoder. First of all, let me tell you, encoder is used to convert one type of signal into another type. It is used to convert one type of signal to another type. In our syllabus, we have two type of encoder. One is decimal to binary, and another is hexadecimal to binary. So children, the logic behind these two are same. Okay. So first of all, I'll be explaining only for decimal to binary, and hexadecimal to binary will be your homework. So is this clear, children? So decimal to binary part I'll be explaining. Now see, some logic we have to know behind this. Okay. So first of all, how many decimal number we have? 0 to 9, that is 10. We have total 10 number of decimals we have. And how many binary number we have? That is 0 and 1, that is 2. Okay, so there is a short formula for this. Same way you can go for hexadecimal to binary also. Hexadecimal has 0 to 9, then A to E. That means total you will be having 16 hexadecimal number. Okay, so now the formula is 2 to the power n greater or equal to I, the simple part. Okay, so 2 to the power n. Now n is how much and I is how much? So I is our input, that is decimal. So in case of here, I is decimal and n is your output. So 2 to the power n means if I take 2 to the power 1, so 2 to the power 1 greater or equal to this I is 10, does it match? No. So 2 to the power 2 if I take, so 2 to the power 2 is how much? 4. It doesn't match. 2 to the power 3. 2 to the 3 is 8. Does not match. 2 to the power 4. 2 to the power 4 is 16. 16 is greater than 10. Condition matches. So condition match. That means here for this part, decimal to binary, our output we got is how much? N value, that is 4. Okay. And input is how much? That is 10. So is this clear, children? So how to take out the input and output? Now let us solve, or let us execute and understand how decimal to binary signals are converted. So see here. So children, see here, for decimal to binary, just now we got n, that is output as 4, and I, that is input as 10, because we are going for decimal to binary conversions. So now first of all, let us go for the truth table. So truth tables for decimal to binary. First of all, I'll write decimal number as input. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In case of hexadecimal, we have to go in the same way. Okay, 9, after 9 it will be A, B, C, D, E. Okay, that total it will be 16. Now for the output part, how many output we have? 4 output we have. So I will be taking as F0, F1, F2, F3. It's not that you have to take F only, you can take any variables. Okay. Now for decimal to binary, that means for encoder, the rule is very simple. First of all, you have to check how many variables we have in the output sector. We have 4 variables. So whenever 4 variables are there, first it will start with 80. I think I have to give some space so that you can understand it properly. Let me make you in this way. So 80 will be there. And remaining, see how many variables are left? 2 variables are left. That will be 1. So for second there will be 40. 4 1, the remaining whatever is left, then 2 0, 2 1, then simply 0 1. Okay, children. So now from here also we have to take out the Boolean algebra expressions. So see here how we take out the Boolean algebra expressions. So see here how we'll take out the Boolean algebra expression. First of all, I'll take out for f0. So for f0, we have to always check for 1. Okay, so 1, how many we have? 8 and 9. f1, f1, we have 4, 5, 6, 7. 4, 5, 6, 7. Then f2. Now f2 part 2, 3. 2, 3. Then here 6, 7. 6, 7. Then f3 part 1, 3, 5, 7, 9. Isn't it? So understood, children, how I have taken out these numbers? Simply in the output sector we have to check the variable as 1 because 1 is on bit and the corresponding input variables whatever is there that will be right. Same thing will be applicable in case of hexadecimal to binary. Clear, children? So now see, next I'll be moving towards this one, logic circuit diagram. Okay. So see here for logic circuit diagram, we have the Boolean expressions. So we'll make a straight line over here like this and we'll give the numbering also. Okay, so children, numbering, I'll be starting from the down or maybe up also. Say 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So there are total 10 numbers in case of decimal 0 to 9. In case of hexadecimal 0 to 9, then A to E. Okay, A, B, C, D, E, F, A to F. Okay, total 6 will be there additional. So now after this we have to use a push button also. This is a push button. Okay, this button is known as push button. And we'll make this straight line over here like this. Use a scale and pencil to make this line properly, neat and clean in your examination, even in your copy also. Okay. So now we'll move toward the Boolean expression. So F0, 8 and 9. So 8 and 9. F0. Okay, 8 and 9. You'll be using OR gate. F0. Then F1, 4, 5, 6, 7. 4, 5, 6, 7. F1. Then F2, 2, 3, 6, 7. 2, 3, 6, 7. All OR gate. And F3, 1, 3, 5, 7, 9. That means 1, 3, 5, 7 and 9. F3. So this is the logic circuit diagram for encoder decimal to binary. Is this clear, children? Now a homework for you. Hexadecimal to binary encoder you'll do by yourself. Okay, children? Thank you.
So your homework will be to do the encoder of hexadecimal to binary. I have did decimal to binary in the same way we have to do for hexadecimal to binary encoder. Hexadecimal contains 16, so 0 to 9 will be 10. Okay, 0 to 9 will be 10, then A, B, C, D, E, F, up to F will be there. Okay, so total will become 16, and 16 there will be 4 output only, and 4 output. The first variable will be 8081, then 4041, 2021, then single 0 single 1. In the same way you have to do, you have to find out f0 f1 f2 f3 the values, then draw the circuit diagrams in the same way. Okay, so in the next video we'll go for decoder and multiplexer.